This is physics paper 42, 0625 IGCSE, May June 2024. A load is suspended and the force 0.75. So this will be simply W equals to mg. 0.75 equals to m into 9.8. So m comes out as 0.077. Okay, don't forget the unit. 77 kg. Mass is kilograms. He says that the load is now suspended with the thread X. There is tension in the horizontal wire to the right side with a force of 1.2 newtons. He says by drawing the scale diagram or by calculation, we can determine the resultant. So there is a force that is acting downwards on the object. If this is the object, there is a force acting downwards of 0.75, and on the horizontal side, this is approximately 1.2 newtons. So we can see that the resultant will be somewhere in this direction, and we can calculate its angle very easily, and the resultant as well. So it is going to make a right angle triangle. So the resultant will be an under root of 1.2 square plus 0.75 square. So the resultant comes out as 1.415 newtons, which we can write down as 1.4. Then he says direction to the vertical. So this is the vertical, and there will be two choices. Either we give this angle or we can give this angle. So we'll choose the smallest one generally. So this will be tan theta equals to 1.2 divided by 0.75, taking tan inverse over there. So theta comes out as 57.99, which will be 58 degrees, the smaller angle. Force may produce a change in size and shape of the object. The shape of the object is basically the chapter of deformation, or you can call this as Hooke's law, if you remember. So he has already mentioned this, which means that we have to give options other than this. So the first one is acceleration, or the change in velocity from the formula F equals to ma, rotation from the formula F into d, moment, and direction in terms of circular motion, as a resultant force is acting towards the center, centripetal force. Acceleration is a rate of change of velocity. I would advise you to add a bracket and just simply write down the formula as well. So you could have written down A equals to delta V slash delta T in bracket for the examiner as a reference. A train has a total mass of 520, 100,000, acceleration is this much. It says that the time taken for the train to increase its speed from this to this. So we have acceleration. The formula for acceleration is V minus U divided by T. We have the final velocity, we have the initial, we have the time for the process as well, and we have, sorry, not the time, but the acceleration. This will be 1.1 equals to 28 minus 15 divided by t. T will come out as, just a moment, t will come out as 12 seconds to be exact, I think. No, this is 11.818 seconds, which will become 12 seconds. Now, please be advised that unit for time is seconds. Calculate the force required to produce an acceleration. So, in this case, it will be simply F equals to ma, the resultant force required to do this job in a mass of 520,000 kilograms. 1.1 would be massive, and this is indeed a massive force. Rounding it off to two significant figures will become 5.7 into 10 raised to power 5 newtons. This force, again, represented with newtons. Train uses electric motors. This is a common question in terms of its theory. Explain why the force on the train due to motors is greater than the value calculated into. So why does the motor has to provide a force greater than this? It's fairly natural that we find that this is the resultant force, which I suspected should have been the case. So the actual force from the engine and all the frictional components, could be drag, could be the friction between the tires and the road, or the moving parts of the electric motor, the resultant force comes out as the engine force minus all these frictional components. So definitely the resultant or the engine force has to be much, much greater than the frictional forces. Only then there can be enough resultant force left to produce an acceleration of 1.1 meters per second square. This is what he's asking. So the engine force has to be greater than the friction and still some. That is why we will justify this, that the extra or the surplus force is needed to compensate or to overcome the frictional or the drag components of this system or of this train. Question number 3 says student drops a heavy ball from vertical height 1.8. The ball falls. It does not bounce, which means that there will be no regaining kinetic or gravitational potential energy. The sharp transfer of energy the ball stores begins to fall when it reaches the ground. So initially, it has the energy stored in gravitational potential. Now, please be advised, we will be using the word store from now onwards instead of forms of energy or transfers of energy. We will say it is being taken from this store. It then gets transferred to kinetic store as it falls and gains its speed. So that's pretty obvious. During the fall, some of the energy is transferred to thermal and internal energy store from the kinetic store. So basically, we start from gravitational potential energy store and it starts with kinetic store. And as it keeps moving down due to air resistance, due to drag, some of the energy that is still being invested from the gravitational store starts to get converted into thermal energy store. So, and another trick question to this is what happens after terminal velocity? So when terminal velocity is reached, the gravitational potential energy store is still losing energy. It is still giving its energy away because the ball is still falling. But the kinetic energy store is not gaining anything more because at terminal velocity, the speed becomes, or the velocity becomes constant. So every single time I calculate half mv squared, I'm going to get the same answer. It doesn't matter. Which means that if the ball is still falling, it's not gaining any speed, it's not observing any change in kinetic energy, so all the gravitational potential energy at that state starts to get converted, or you can say it is now being stored in thermal energy in the object as it keeps falling down. But again, that's a tricky question for an MCQ. Calculate the maximum speed of the ball, ignore the air resistance. A very easy and very repetitive question. So the starting point would be that the change in gravitational potential energy store will lead to the change in kinetic energy store. So mg delta h, the falling height, should be equal to half mv squared. So mass gets cancelled out from both sides. The gravitational field strength is 9.8. The height it was thrown from is 1.8 meters. 1.8 equals to 1 over 2. 2 comes over to this side, being multiplied over here. So I can remove the 2 from here. And then I'm left with v squared. Be advised and be very careful. You have to take the under root at the end. This is where students make the most common mistake. So after taking the under root, your final answer will be 5.9396. I will round this off to 5.9 meters per second. Please be advised it is the unit for speed. Don't miss it out. Question number 4. Two-phase evaporation differs from boiling. So again, you can give a comparison. You can give pointers. It's your choice. So evaporation only happens at the surface. Boiling happens throughout the liquid. Evaporation happens at all temperatures, even at colder ones, but boiling happens only at a specific temperature. This is a bit of information that's a bit on the more proper side of physics or accurate side of physics, but this is what happens. Even when something freezes, let's say water has frozen below 0 degrees centigrade, we would still consider this as evaporation. We only consider evaporation not taking place at absolute 0. But again, that's a theory. We haven't measured it. Shows the part of the container used to store a mixture of liquid and gaseous oxygen. So there should be some liquid in this and some gaseous, let's say, oxygen in it. Steel walls, and there's vacuum. Okay. So it says determine the temperature of the liquid, oxygen, Kelvin. So very easily, we have Kelvin equals to degree centigrade plus 273. So this will be minus 160 plus 273. The actual temperature in Kelvin is going to be positive, I think, plus 116. Sorry, it's 113. Yeah, so it's going to be 113 Kelvin. Yeah, so this is 113. Now notice that in some questions, for example, temperature, Kelvin is already given. But I would still advise you to keep an open eye, because in some questions you can see that the unit was not given, it was expected from you. So please be careful. He says, state two methods in thermal energy transfer that vacuum prevents. So vacuum prevents conduction and convection because both of them need a medium, need a contact between transferring medium for this process to exchange thermal energy. Describe in term particles how gas. Now, this is again a repeated question. I would advise you to just memorize the statements if you are unable to figure this out on your own at all times. So he says how gas exerts pressure on the walls of container. Let me show you in animation what's actually happening. So there is a common misconception among students that probably the gas particles are colliding with each other somewhere central in the central region. The gas particles are colliding with each other. We don't disagree on that. The main problem is that this is not the reason for gas pressure. The reason for gas pressure is when these molecules collide with the walls of container. That is where we are interested to find the exact pressure. What's happening at the center is not my problem. What's happening anywhere else is not my problem. Gas molecules are colliding with each other, but this is not going to be mentioned in the answer. So how do we justify this? So this is the wall, the particles are colliding, and then they're bouncing off. When they do that, they experience a change in momentum. A change in momentum in a certain time, which leads to force. And force on an area becomes pressure. This is the entire story. So how to justify that? So we say the particles collide with the walls of container and maybe add that they are in constant random motion. Because they're in constant random motion, we expect them to collide with the walls of container. Now, you might write down under exams pressure that they're colliding with each other. Mind you, this is incorrect. They are colliding with each other. There's no disagreement about that, but it's not exactly responsible for the pressure. So during collisions, they exert a force on the walls due to change in momentum. This is what mathematics or physics tells us, right? Okay, so the second part would be this, and then the force on an area. This is the conclusion. So force on an area makes the pressure of the gas. Or you can justify this by this whole mathematics in a single statement that the rate of change of momentum, which is of course delta P divided by delta T per unit area, which is of course equal to force. So per unit area makes the pressure of the gas. Again, a different way of saying the same thing, but that is exactly what's happening. So question number 5, this was interesting in terms of its application. So I'm going to zoom out a bit because I need more space to work. Okay, so we have prism ABC, yellow light. It is entering at 90 degrees. These are just initial observations, but let's see how the question goes. He says, explain why the ray does not change direction, and the only reason is the angle of incidence is 0. Whenever the angle of incidence is 0, or it enters at perpendicular angle to the surface, it generally does not bend. But do we say this is refracting or not? You see, generally when we use the definition of refraction, we associate this idea with bending of light when it changes medium. There is no bending happening at this point, but should we still qualify this as refraction? Yes, we do, because refraction, the true understanding of refraction is actually a change of speed when an object, when the light ray observes a change in medium. So bending is under special conditions. It bends or not, it depends on the angle of incidence. But always you will experience that there's going to be a change in speed because of change in medium. So I will have to refer this as refraction. So it is refraction when it goes from this medium to this medium. But anyways, these are just initial observations. He says the critical angle is this much. Calculate the refractive index. A very straightforward formula. N equals to 1 divided by sine of C. N equals to 1 over sine of 42. If you calculate this properly, your answer is going to come out as 1.5. So refractive index is 1.5. He says continue the path of the light ray. Now, it's a 3-mark question. It may not be as straightforward as you might think. If you're tempted to draw this light ray out of the medium, I would suggest whenever you're tempted to do that, first draw a normal and then make a decision whether this light ray is going to exit or is going to stay inside. You see, this is a dense medium right now. So whenever light exists in a dense medium, you have to be careful about its trajectory. Now, in terms of its trajectory, it is in dense medium, and for total internal reflection, this is what this will be the first hint that I will get in my head. So, first thing is it needs to be moved from dense to rare, or it needs to try to do that. Is it trying to do that? Yes, it is. So now I should pay more attention to this. I'm expecting that it might be undergoing total internal reflection, but let's see. The angle of incidence should be much greater than critical angle. Now, the critical angle we have been given is 42. If I come here and I realize that with the normal, which is the blue line, if I measure the angle of incidence, it's much greater than the critical angle because it is much greater than 42. It is even greater than 45. So this condition is also fulfilled. Now, because of that exact idea, it is trying to move from dense to rare, angle of incidence greater than critical angle. I will assume, or you can say that my conclusion is it will undergo total internal reflection, and entirely precisely because of that, it will not be able to exit, rather it will stay inside the same medium. I will do this inspection by eye. Of course, I will just guess it and try to make sure that the angle of reflection is also the same. Now, naturally, if you do that with a compass, if you do that with a protractor, you will realize that this eventually enters at or meets side A and C exactly at 90 degrees or roughly at 90 degrees. So at this point, it will, of course, exit the prism. This is exactly what he asks us to do, that it leaves the prism. Continue what you think should be done until it leaves the prism. So that is how it's going to be. Internet data transfer, again, a repeated question. Benefits of optic fibers. So high rate of transmission of data carries large amount of information. It's secure, where you can't hack it directly as you used to do in copper lines. Low signal loss, low data loss, low signal degradation. Transparent to infrared, so we use infrared. And infrared can easily pass through least loss of energy through the optic fibers, again, based on memory. So he says pressure time graph for sound wave, which is longitudinal. Now, be advised, we're dealing with a longitudinal wave. If you look at the movement of particles of a sound wave, this is what they're going to look like. So sometimes they move. Now, even in a certain instant, you can see that the particles are close to each other around this area. Wherever they're close to each other, that's a compression phase. Pressure is a bit higher because they're close together. And wherever the particles are further away from each other, this is a rarefaction phase where the particles experience a slightly low pressure. But again, the pressure is not zero, it's just below atmospheric pressure, very minutely so. So when we go back to this graph, this is atmospheric pressure, which is rightly said as 10 raised to the power 5 Pascal. It's quite possible that this comes out as 1.3 into 10 raised to the power 5 Pascal, slightly above atmospheric pressure. These are my compression phases when particles are coming close together. And over here, I might have particles slightly below atmospheric pressure, might be 0. Let's say 8 into 10 raised to the power 5 pascals. And this is where particles are moving away from each other. So rarefaction phase. This is what he's asking us to do. And we have mentioned that since he mentioned just one, we've done for both. Again, no problem. Now, be advised that this line does not represent zero pressure. This represents atmospheric pressure. For example, if no sound was being produced, what would have happened to the air particles? They would have stayed in their own positions, or they would be vibrating or randomly moving through air, producing atmospheric pressure. Explain why this graph cannot be used to find wavelength. Now, the problem is they mentioned time on the x-axis. If I wanted to measure something, I can measure the frequency, or I can calculate it by choosing from compression to compression or time from rarefaction to rarefaction. I can do that by using 1/t, but I can't measure the wavelength because they haven't mentioned a displacement. So it does not show variation changes in displacement along the x-axis. That is why we can't associate these lengths as wavelengths. We can't do that, but we can use them for time periods and find the frequency if it came to that. So the sound becomes louder and lower pitch. So he wants to access this part of information from your brain. That do you remember that loudness is actually associated to the amplitude and pitch is actually the frequency. So a standard sound wave, if this is what it looks like, if it had been louder, then the amplitude would have increased without a change in frequency. It would have had the same number of waves. That is what happens when you increase the volume when you're listening to music on your headphones. So you're making it louder, but you're actually making the amplitude of the wave larger. And in terms of lower pitch, pitch is an alternative word for frequency. So if the pitch is decreasing, that means the frequency is decreasing, which means that it will be expanding in terms of, let's say, time. So increases, or amplitude increases because it's louder. Frequency decreases because pitch is just a different name for frequency. So if it's a lower pitch, then the frequency is also decreasing, or it has decreased. Frequency is given, speed is given. We can find the wavelength as V equals to F lambda. Now you might be wondering why this question is for 3 marks. Take a pause and try to figure out why that may be. You see, the extra credit is for this kilohertz, if you were able to figure this out or not. So V, it is already given to you as 1500 meters per second. Frequency would be 13,000. Or you can write this down as 13 into 10 raised to power 3 multiplied by lambda. Lambda will come out as 0.1158538. 538 meters, which will, up to 2 significant figures, become 0.12. If I leave my answer like this, I will be penalized for this. So since it is length or wavelength, I should add meters. Approximate speed of sound in air. Now, a common misconception at this point was, since the students read the word speed, they sometimes wrote down the speed of light in this position, in this place. He's asking for the speed of sound in air, which it ranges from 330 to 350. So writing down 330 without the unit would lead no marks. Again, speed, be careful about the unit. Question number 7. This is a bit tricky in terms of how to phrase this, how to write this in proper English, but otherwise the concept was very simple. He says there are 3 steel bars. 2 of them are magnetized, which means that 2 of them are definitely bar magnets. So for the sake of example, if this is bar magnet 1 and bar magnet 2, one of them is unmagnetized, which means C, or it could be for that matter, B or A, was not magnetized. Explain how the student can determine which piece is unmagnetized using only the 3 pieces of steel. So the apparatus is in front of us, and this is what we have to do. So it's going to be a logical problem, how to approach this. So bring one side. First, we test A with B, right? So on one side, it should be attracting, and from the other, it should be repelling. So we can fix the rod B in its own position. So first we bring in rod A from, let's say, side X. We see if this was north, it would be attracting. And then we bring in side A again from side Y, the other side, which is south. Again, we don't know what poles they might have, so we might have to label them X, Y, or P, Q, and so on and so forth. So when we're doing that, the south, if it encounters south, will repel. So that will give me the guarantee that A and B both are magnets. If I had done the same thing with C, which I'm suspecting in this case is not a magnet, then if I brought north or if I brought south, it would be attracted by both ends. It wouldn't have repulsion in any orientation, which would tell me that this is unmagnetized. And since it's made of steel, there will be some attraction in C. That is how we've described it, and you can pause the video and try to take a read. You can also read the marking scheme about this question. That is how they've tried to justify it. It could have been B and C are magnetized and A is unmagnetized. Again, you can choose any letters to justify your answer, but the logic remains the same. The next question is about the step-down transformer. Now, how do you know that this is step-down? Because the output side, where you take the energy from, has a low number of turns visually as compared to the primary side, which is the input side of the transformer. This side is connected to the source or AC source, where the power is going to be drawn from. This is your source. This is your switch or the plug that you just plug into your wall adapters. And the output could be a laptop charger, could be a phone charger, and could be an appliance that you're trying to use from the source. 100% efficient, the transformer is supplied. The main voltage is 240, output power is 45 watts. Calculate the input current. So this will be P equals to IV. 45 watts of power being demanded. Current is what we don't know. And the input voltage is 240 volts. So the current demanded from the supply, from the power supply company, will be P equals to IV. And This current will come out as 0.1875 amperes. Please don't forget about the unit. This will be 0.19 amperes. Question number 2, draw a label diagram step down transformer. A label diagram would require that you draw a core properly. You don't have to draw this in 3 dimensions. You can just draw this in this fashion. Have more number of turns deliberately drawn on the primary side and label it. So you can label this with an AC supply signal that this is my primary side. Of course, I'm missing some steps of rewriting so that we can save more time. And visibly make sure that there are less number of turns on the secondary side. So you can connect a bulb, or you can connect an appliance, or you can just simply call this as secondary side. Then, since we're talking about, I think we're talking about materials, so it would be a good idea that you mention that this is soft iron core. And you mentioned that these are copper wires or made of copper. These are also copper wires. And of course, it is advisable to use a ruler for these diagrams. Also, as an improvement, again, not required, but as an improvement, you can indicate that this side has more coils and this one has less number of coils. Next is question number 8. A circuit shows the circuit is designed to switch on at designated times when the surroundings are dark. Okay. Draw a symbol for the voltmeter to measure the potential difference across the LDR. So this is our LDR. So we can draw the voltmeter like this, or we can draw the voltmeter on the other side like this. But you have to leave only one option, so I'm erasing the other one. State, it says surrounding is now become dark. So we know that the trend for an LDR, which is from your course, is inversely proportional to light. If light intensity decreases or it becomes dark, the resistance of the LDR increases. That is as simple as that. So this point was from memory. I can't do anything about that. State and explain the effect of change in PD across the light emitting diode. Effect of this. Now, you see, the resistance has increased for this component, and the LED and resistor are in parallel combination. So, by a simple mathematics check, you can verify that if we try to write down the formula of 1 over RT plus 1 over R1 plus 1 over R2, this actually narrows down to R1 product R2 over R1 plus R2, product over sum. This is a shortcut for 2 elements, whatever resistance of this component may be. So the resistance of one of the components is increasing, although its in numerator is also increasing, but we need to respect mathematics that the multiplication increases much more rapidly than simple addition. If it had been 100, 100 squared would be much greater than 100 plus 100. That is what we are absolutely sure about. So the total resistance pair combination increases, and this causes the potential difference to increase across the whole combination, which eventually state and explain the effect of this change, which will also increase the voltage. And of course, since we have connected the voltmeter across it, the voltmeter reading increases. This is what we will observe. Part B, he says we have lamp A and B. They are identical filament lamps. They will be drawing currents of their own demand from the same branch. Then they will be divided. So he said by the power supply 0.5. So power supply provides 0.5 amperes of current. Since they are identical, the current will be divided equally up to this point, at least, to my understanding. He says calculate the resistance of lamp A. Now, since they are connected in parallel to each other, they have equal access to voltages on both sides. So we can simply use the equation V equals to IR, 240 volts equals to current, which is 0.25 into R. So R comes out as probably, let's just see what's the value is going to be. So 240 divided by 0.525, sorry, 25, which is 960. So that is, yep, that is the resistance of one lamp. Yep, 960 ohms. This is one way of doing that. Let's look at another way. So if we were to assume this to be a single resistor component, a carrying current of 0.5 amperes with 240 volts, we might have assumed that this is V equals to IR and 240 equals to 0.5 into R. R would come out as 480 ohms. Now I know that this is actually 480 ohms for both of the elements. So I would have had to reverse track my way to this formula, plus 1 over R2. Now since I know that they're both identical, I can very well say that this is actually R plus R. And this RT would become 480. So 1 over 480 equals to 1 over R plus 1 over R. This would again lead to R by 2 equals to 480. And then R would become 960 again. A counter logic would have been that if the total resistance is 480 for this one, I know for a fact that if they are identical, the resistance would have been halved by the formula RT equals to product over sum, which is R1 multiplied by R2 divided by R1 plus R2. The same formula I was talking about over here, which comes from just two resistors. This is a shortcut for two resistors. So again, many logics available here, but the final answer will be 960 ohms. Please don't forget the unit. The last question is from radioactivity. He says 2 safety precautions for isotopes to be medical procedures. So we need to have large distance between the source and the person who's using it, and this reduces the amount of radiation to the person. Add shielding effect, either wear hazmat suits or add more layers of lead shields between the doctor and the patient, because shielding would make sure that majority of the radiation is absorbed. We can choose elements with the shorter half-life, so this reduces exposure time and also puts the patient at lower risk, because the radiation absorbed by their bodies would also be released quickly, or it will lose its intensity if it has low half-life. Dosimeter badges, again, we use it for the personnel working with these machines, but we don't really use that for patients. But we can do that, but it's not limited to. Give 2 reasons why alpha emitters are not used in radioactive tracers in the body. You see, alpha radiation is very ionizing and it is very absorbent because of its size. If you've ingested it, if you've eaten a source that has alpha, it wouldn't be able to come out of your body because it will be instantly absorbed by your cell tissues, because it cannot even pass through a piece of paper. It is so big in size that it can't even pass through a piece of paper. Then how can it pass through your body? So that's why we are saying that radiation would not be able to detect on the outside because it is being absorbed in the inside of the body. That's the problem. If it is being absorbed inside the body, then this will definitely cause radiation sickness or cell mutation or gene mutation, which will make you sick and eventually cause death. So sodium-24 is an isotope of sodium with 11 nucleon number, or with 11 proton number and nucleon 24. It emits a beta particle and becomes magnesium. So let's make an equation. This is what he wants us to do, nuclide notation. So we start with sodium with 24, 11, breaks down to become magnesium with 24, 12 plus beta 0 minus 1. Now notice that you can start from this location, like this one. We have to memorize the atomic numbers and atomic masses for beta, alpha, and gamma. Beta is 0 minus 1, alpha is 4, 2, and gamma is 0, 0. Just for a reminder, neutron is 1, 0, proton is 1, 1. And this is for beta. So we can then use algebra that charges are conserved. So over here we should get 24, because 24 plus 0 should be 24 on the left-hand side. So everything has to be balanced. On the right-hand side, we can say this is 11 and this is minus 1, and let's keep this as x. Treat this arrow as an equality, so this will become x plus minus 1 from beta and 11 from sodium. Now, when this minus 1 goes to the other side, this becomes x equals to 12. That is why, if you notice in the previous when I was giving out the answers, this was actually written down as 12. And the mechanism of that is, again, a part of your course. What happens to sodium inside the sodium atom, that there is a beta or negative electron, and there is an increase in proton number. So basically, a neutron inside the nucleus disintegrates to become a proton and an electron. Electron is ejected out as beta emission, ejected as beta, and proton stays inside. It stays inside the nucleus. That is why from 11 protons, today we have 12, because we have one more proton, because a neutron disintegrated to become a proton. Electron gets ejected as beta radiation. This is what we get on the outside. This mechanism is also a part of your course. The solar system includes sun. Again, the whole chapter is based on memory, very less logic in this. State 2 of the times of natural orbiting the sun. So dwarf planets, comets, and asteroids. State the shape elliptical, generally elliptical. He says orbit of the sun, point A, object is closest to the sun, at point B is the furthest away. This is a repeated question in terms of elliptical orbits and how to address these issues. He says, state and explain the energy transfer as the object travels from point A to B. Now, it could have been like this, or it could have been like this. For the sake of example, I am choosing this rotation to go something like this. It could have been the other way around. It does not matter. Whatever orientation suits you, suits your brain, is fine. Now, since it is very far away in case of B, I will say that it has a lot of gravitational potential energy. When it starts coming towards the sun, we do generally call that it is falling towards the sun. And we know that if something falls in the presence of gravitational attraction, the gravitational potential energy gets converted into kinetic energy. It is gaining speed, and precisely that is what happens when you throw an object from height. Its gravitational potential energy store starts giving its energy to the kinetic store. And when it reaches A, it would be the fastest. Its kinetic energy would be the highest in its whole life cycle. So that is the basic gist of it. So statement, energy from kinetic store decreases. Okay, so it's traveling from A to B. So we'll go the opposite way, from A to B. So its kinetic energy will start decreasing, and gravitational potential store would start increasing. So energy from kinetic store decreases and is given to the gravitational potential store as it increases. In the explanation, energy is always conserved. So it's always going to be balanced between, or it's only going to be it's going to bounce between kinetic and gravitational for a system like this. When it comes to B, again, the opposite thing will happen when it starts falling back down again towards A. Jupiter is 7.8 meters from the sun. Light travels this much. Count the time taken for the sunlight to reach Jupiter. So it's simply speed equals to distance over time. Speed is 3 into 10 raised to the power 8. Distance is 7.0 into 10 raised to the power 11 meters, no kilometers. Be careful. Divided by time. So time equals, if you calculate this, this comes out as 2600 seconds. So this will be 2.6 into 10 raised to the power 3 seconds. Please be careful. Unit are seconds. The next part is again from memory. Name the galaxy Milky Way. Light is observed. Say that the universe is observed, that this observation supports redshifted. That is a Big Bang theory. If we hadn't known redshift occurs, we might not have been able to backtrack our way to Big Bang theory. Cosmic background radiation is observed in all parts of the space. Again, a memory-based question. You'll find exactly this statement in your book as well. State what is when this radiation was produced. So shortly after the Big Bang theory or Big Bang explosion, this radiation was released. So if we can detect these cosmic microwave background radiations, we can most definitely say how old our universe was. So explain why this radiation is now microwave region. Again, it was not at the beginning, but now it is, because everything is moving away from each other. If everything is moving away, it will be redshifted, which means that the wavelength starts increasing of those radiation or of those waves that we were expecting to see. So due to redshift, as the universe is expanding, the radiation shifted to the microwave spectrum region, or the microwave spectrum on the radiation level from, or the radiations from gamma up to radio. it is moving towards the microwave region. That is all for today.